Alors, bonjour à tous, mon nom est Jérôme Lavoué. Je suis professeur au département de santé au travail et santé environnementale et santé au travail à l'école de santé publique de l'Université de Montréal. Ce séminaire va être présenté en anglais. Je souhaitais m'adresser en français à notre audience francophone locale au début de la présentation. Donc, ce séminaire se déroule grâce au Centre de recherche en santé publique de l'école de l'Université de Montréal, le CRESP. Alors, merci au CRESP. Si j'avais un t-shirt CRESP et une casquette CRESP, je les porterais. Attendez. And bienvenue aussi à notre audience en ligne. So I'll switch to English now, as our distinguished speaker is Anglophone. So today we are welcoming Dr. Susan Arnold. Okay, I switch to the right text. So Susan is a professor at University of Minnesota School of Public Health, from which she received a Ph.D. in 2015. Dr. Arnold is also director of the Exposure Science and Sustainability Institute at the University of Minnesota and of the Midwest Center for Occupational Health and Safety. She specializes in the development, evaluation, and application of mathematical models to estimate exposures in new occupational environments. And among several other things, Susan is very well known for her work on exposure decisions and her involvement in the development of the tool called SDM, now in its second version. And it's an Excel-based, user-friendly tool for estimating exposures. And I think we'll get some more details about that in the next hour. And so thank you very much for coming here and speaking to this audience locally and online. And your turn, Susan.
All right, thank you so much, Jerome, Maximilian, and everyone. I've had such a warm welcome. It's really delightful. It's an honor to be here. So I've packed a lot of material to cover in 90 minutes, so I'm going to jump right in. It is set up to be somewhat interactive, as much as we can with a hybrid session. So for those of you on Zoom, we've tried to use some functionality that hopefully you will also be able to take part in. And I just wanted to mention quickly, I forgot to put the link in the slides, but much of the material that I'm going to cover, albeit quickly, is also covered in a series of modular videos. So they're narrated videos. They're online, so again, I'll send the link of where you can find those. But for the technical concepts, as well as the modules on how to use the tool step by step, that's all available on the website and on YouTube for free. So there's a backup if I go too fast. All right, so this is about improving exposure judgment in industrial hygiene, occupational hygiene, and I'm going to specifically focus on the components that relate to the structured deterministic model. So I will touch on some of the topics, but very, very briefly. And I want to say thank you to Dr. Sparrow for his talk this morning, because he very graciously covered some of the topics that I don't have time to go over. So for those of you that were able to attend his lovely and wonderful presentation this morning, will have had some of that. Let's see, get this off the screen. No, will that go away?
I'm sorry.
You can just, if you want. Oh, perfect. Okay. Great. All right. So what I hope to cover in the next 90 minutes is just briefly the agenda, the use of the interactive technology, which today is Poll Everywhere. I'm going to make the case for improvement, but again, it's going to be very focused. So we could spend the whole 90 minutes going over the science and the evidence for why we need to change how we approach exposure assessment, but I'm going to hit some of the key relevant points here to lead us into an introduction of the structured deterministic model. And so what I'm going to do is I'm going to cover the algorithms, the basis for the algorithms and the logic behind the tool, and then briefly introduce you to the tool itself, so how to navigate through the Excel-based tool to be able to use it. And then I just wanted to mention that the tool is freely available, and the way that you do that is you go to the link that's shown here. I will make my slides available later, but you can go to the University of Minnesota website and download click on the link to execute a license. And once you do that, then you receive an email with a link to both the tool and the support file, and then you're able to use it freely within the conditions of the license. Finally, I will demonstrate using a couple of case studies, how the tool kind of automates the algorithms and what your role is in interacting with that tool. So, still have that box.
Yeah, great.
Okay. Okay, so as I mentioned, we're going to use Poll Everywhere, and it's very helpful for me to get real-time feedback from you as for everyone else to kind of learn from their peers. And so using Poll Everywhere, there are a couple of ways to respond. I'm not sure if anybody's on their computer. There is a web link, it's shown here, but you can also join by text. So the number that you're going to text to is 22333. And then the message that you're going to put in your text message is Susan Arnold 390. Give me a wave when you've been able to do that. So the number, so the text number is 22333. And then the message is Susan Arnold 390. Is it working?
Yeah.
I have one person in. It's not working. Is it not going through?
Yeah.
It's not working.
This number is inactive.
No, it shows,
Some people are in. That's weird.
shared it's working online for the link.
The link is working. Okay, yeah. But someone has gotten in on their phone, right? Oh, no. Danielle, are you able to get in on your phone?
It's not working on my cell phone. I'll try the web link.
The web link was.
Okay.
Just no way.
That's it's technology. So I checked on my phone this morning and it worked, but okay, well we'll do the best we can. All right, so here's the real test. Oops. Oh, wait a minute, I don't want to do that. You guys have you already responded? No? These are somebody else's responses. Okay, so just to all right. So just to get used to using the tool, the question is, if someone paid you to study any subject, what would you study? And so you can type in any topic of interest, and let's just see how that works. All right. there we go. I'm happy to see hygiene growing in size. But this in itself is a really interesting example in that it's learning. And then look at we were at a webinar in a Department of Occupational and Environmental Hygiene with people studying similar kinds of, following similar career trajectories. And yet look at the variability, look at how broad the interest level is across this group. So we're going to come back to that. And all right, you can keep putting your responses in. I'm going to get started here. Okay, so as a starting point, when we think about occupational exposure assessment strategies, we really need to ensure that the design of our exposure assessment strategy reflects or is driven by the reason for obtaining samples or the reason for conducting the exposure assessment. So we want to make sure that the approach that we take has the power to answer the question that we're seeking to answer is another way to think about this. So for example, if we're conducting routine monitoring of worker exposures to chemicals in a workplace, and then comparing them against an occupational exposure limit, in other words, in sort of a compliance mode, we would use a specific approach, but that would be different than an exposure assessment that we're conducting where the goal is to determine the relationship between exposure to some agent and the health outcome, such as for informing an occupational epidemiology study. So again, we want to make sure that the strategy that we choose aligns with our objectives for conducting that study. And overall, our goal, what we're trying to do is to ensure that no worker has unacceptable exposures, that no one is overexposed. And since we know that exposures vary between workers over time, across work shifts and across locations, then if our exposure assessment includes sampling, we need to ensure that our sampling strategy will be effective in capturing this variability. We need to make sure that it has the power to capture that variability so that our exposure profile represents the true worker exposure. But at the same time, that strategy has to be both feasible and efficient. So meaning that it shouldn't require such a large number of samples that it's just not economically feasible, or that the time that it takes for us to collect those samples, analyze them, analyze the results and draw some conclusions isn't a longer period of time than the time frame within which we need our results. And our reality is that occupational hygienists usually always operate within limited resources. We always have limited budgets. And so because of those cost pressures, it's very rare that we're able to collect a large number of samples. Our sample sizes are almost always small. So just talk very briefly about similar exposure groups. Within a population of workers, we know that if we take a closer look, we know that within that population profile, there are in fact many kind of subgroupings of exposure profiles, which we call similar exposure groups. And the similar exposure groups, just very briefly, are groupings of workers that we believe will have a similar exposure profile because they're working in a similar environment, in a similar around a similar work process. Their work tasks and their duration of their work in that area is similar, and so on, so that the factors that would contribute to their exposure are similar. We believe that their exposures will be similar, and we can group those. Together into those workers into one group. So this, and again, this facilitates the efficient exposure assessment of a large number of workers because we're grouping them in such a way that we're capturing the between and within worker variability. And again, if our strategy includes sampling, then by randomly sampling the workers within that similar exposure group, we can develop an exposure profile. We can capture, characterize that exposure distribution in a way that represents the true exposure. Okay, and again, within an exposure assessment where, like an industrial hygiene example, where we're looking at characterizing an exposure profile and comparing that exposure to some sort of benchmark, just to give some examples, we might judge that profile to be acceptable if all the measurements in the data set are below the occupational exposure assessment. In fact, in the US with the OSHA framework, that is what is done. The measurements are compared to the OEL and a decision is made regarding the acceptability of the exposure. Another approach might be if all the measurements in a data set are below an action level. So action levels vary very typically about half of the occupational exposure limit. We might use a different decision metric, such as the 95th percentile, and so that when all of the exposures, when the 95th percentile of that exposure profile is less than the occupational exposure limit or the action limit, we draw a conclusion of acceptability. Or we might look for an exposure metric to fall in a desired exposure band. So, okay, hopefully our program works. But now I need some input from you. Let me just open up the poll. Okay, so if an employee performs a job 100 times a year, and you collected samples across every time that happens, across all 100 of those work shifts, in your opinion, in your professional judgment, how many times is it acceptable for the exposures to exceed the occupational exposure limit? And assuming that worker is not wearing a respirator, or those workers are not wearing respirators. So I think you can read that. So answer A is 0 times, 0 samples can be over the exposure limit. B is 1 sample or 1 exposure in those 100 work shifts. C is 5 samples or 5 times in the 100 work shifts. D is, D is 10 times, and E is 25 times, and F is 50 times. So let's see. The responses are coming in, and I'll switch to show the responses in just a second. So let's see what we see. Okay, so again, really interesting. We have about, let's see, I think we have about 50 people online and about 20 people in here. All very, very, very well-trained, smart, competent professionals. And yet we have 3 different definitions of, or 3 different levels of acceptable exceedances, which is really interesting. So the majority say it's never acceptable to have a measurement over the exposure limit. And then second highest is 5 samples, 5%. So, all right, well, let me ask a follow-up question then. Wait a minute until I open up the poll. Oops. So the second question is, what's the most common number of air samples that are used to make a judgment about exposure? In other words, how many measurements do we typically have when we make exposure assessment judgments? And again, I'll in case you can't see the numbers. So A is more than 10, B is 6 to 10, C is 3 to 5, D is 1 or 2, and let's see, do we have an E option? We do. E is 0. Somebody's hedging their bets there. We had 29, now we're down to 28. Let's see what that looks like. Okay. A little bit of shifting going on, but most people believe that the most common number of air samples used to make a judgment about exposure is 6 to 10 samples. And it's interesting that we have, again, a very wide-ranging understanding of how many samples we typically use to make exposure assessment judgments. Okay, so 9% thought that the most common number is 0. And that's right. The most common number of samples used to make exposure judgments is 0. For the vast majority of the assessments that we have to conduct as industrial hygienists, we do not have the luxury of having exposure measurements, personal exposure measurements. So bear that in mind as I show you this graphic. So, and actually, let's come back here for a second. Okay, so the most common number is actually 0. The next most common number of samples is 1 or 2. And the next most common number is 3 to 5. But there's a huge lag between 0 versus 3 samples. Okay, so now let's just keep that in mind. Oh, so again, we are compelled for a number of reasons to make judgments without a robust set of personal exposure measurements. So in this table that was created by my colleague Mark Senzel, let's set up the scenario. So the occupational exposure limit is 10. The geometric standard deviation for this exposure profile is 2.5. So pretty commonly encountered in industry. And the action limit is 5, but in this case, we're going to be thinking about this exposure limit of 10. And so for this scenario, in this first column labeled EF, that stands for the exceedance fraction, we can see 4 examples of different exceedance fractions or different levels of exceedances. So this first one, yes, you can see, great. So this first 1.5 or 50% exceedance fraction. So this is the true exceedance fraction for a given geometric mean and geometric standard deviation and hence 95th percentile. And then on the right-hand side of the table, we see the percentage of time or the probability that all the measurements in the data set will fall below the occupational exposure limit. And then we have our scenarios. We might have a data set of 1 up to, so 1 or 2 or 3 or 4 or 5 measurements. All right, so I want us to focus on this, on this second scenario where the true exceedance fraction is 25, it's 0.25. So 25% of the exposures are above that 95th percentile. The 90th percentile is such that 25% of the exposures are greater than the OEL, which means that the converse, 75% of that profile is less than the occupational exposure limit. Would you agree that a 25% exceedance fraction is unacceptable? Can we agree that that is just too high? Okay, so we would want to know that our strategy has a very high probability of detecting those exceedances so that we would conclude that that exposure is unacceptable, right? Does that make sense? Okay, so if we followed a common practice or followed kind of the OSHA approach and we collected 1 sample given a true exceedance fraction of 0.25, 75% of the time that sample would be below the exposure limit. And we would conclude or be tempted to conclude that that exposure is acceptable. If we collected 3 samples, then again, 42% of the time, there's a 42% probability that those 3 samples are going to be below the exposure limit. So even though there's a 25% exceedance fraction, we would conclude that that exposure is acceptable. So I hope that when you hear people talking about collecting 1 or 2 samples to make an exposure judgment as the primary source of information, this gives you nightmares forever forward. I mean, it's not a robust approach. It's not an appropriate approach. And in a couple of minutes, I'll show you from the studies that were conducted what one of the consequences of this is. And again, a lot of it relates to the way in which exposure measurements, exposures are distributed. So we have this, instead of having this very symmetrical distribution in the profile, we have a skewed distribution. We have this typically log normal distribution, and our brains are they're not wired to intuitively grasp that skewness. And so psychologists believe that what happens in that case is we don't adequately account for that long tail in the distribution. And in cases of exposure data, if we don't have the guidance of a robust data set and the proper analysis, then we're likely to underestimate that upper tail of the exposure. All right, but I'm drifting off course here. Let's get back on track. Okay, so we really need to be efficient with our resources. And one of the ways that we promote this is by following this exposure assessment strategy that was developed and published by the American Industrial Hygiene Association, or AIHA. And the process works starting with the basic characterization. So gathering the necessary information about the work environment, the work and the work tasks and the worker to have the information at hand to be able to develop that exposure profile. And then from there, once we have that information, we can conduct our exposure assessment and draw some conclusions about the exposure profile, the acceptability of the exposure profile. So we may have enough information to conclude that the exposure is acceptable or unacceptable, or we may find that in fact we don't quite have enough information, that we need some more, there's something more we need to understand, or we need to collect a little more data, in which case the process is intended to be cyclical or iterative, so that we can iterate through this process until we come to a conclusion, or until we're able to identify what our follow-up actions need to be. And in this strategy, we express our judgments categorically as probabilities. So we have this exposure control framework with, depending on which one you're using, the number of categories vary between 4 and 5, and you'll see as I show you the tool, we're advocating for an expanded framework. But basically it works like this. We want to indicate the likelihood that the 95th percentile falls into a particular exposure category. And the category with the highest probability is the most likely exposure category. The exposure categories themselves represent fractions of the occupational exposure limit. So for example, category 1 exposure here would be less than 10% of the OEL, whereas a category 4 would be an exposure profile with a 95th percentile that is greater than 100% of the occupational exposure limit. And one of the ways that we make that determination is by collecting some personal exposure measurements. So in this example, we have 3 measurements. From those 3 measurements, we can calculate a 95th percentile and then compare that 95th percentile estimate against our occupational exposure limit. And in this case, you can see our OEL is 10, our 95th percentile estimate from that exposure profile is 10.5. It's greater than 10. So we would conclude that it's a category 4, and from our Bayesian framework, we would see that in fact in this case there's a 50% probability that it is a category 4 exposure. Okay, but I just finished telling you that most of the time we don't have exposure monitoring, we don't have exposure measurement data. Most of the time we have to make decisions about the acceptability of exposures without those measurements. We still want to be using that systematic, that decision metric, and very commonly it's that 95th percentile, but we have to use other inputs. We have to use other tools, such as mathematical modeling, for estimating the exposures to make that assessment of acceptability. And then following on with that, we take sort of a systems approach to risk management such that similar exposures with similar health effects, so similar health risks, would then be treated similarly with respect to risk management. So we would want to drive the same or similar actions for similar levels of exposures and health risks. So I've used these terms a couple of times. I've talked about an effective strategy. And just to be clear, an effective strategy is one which has the ability to, or gives us the ability to reach a correct decision. So it's a strategy that's going to empower us to draw the correct conclusions about that exposure. An efficient strategy is one that will allow us to reach a correct decision with the minimum number or a tolerable expenditure of resources. So again, we want to use as few resources as we can, but still reach the right decision. We want to have a high probability of detecting a clearly unacceptable group exposure profile. So, and again, we want to do this because we want to minimize the number of workers whose upper percentile exposures are graded in the OEL. Said another way, we want to minimize the number of workers that are going to be overexposed. So given that we know that most of the time we aren't able to collect exposure measurements, personal exposure measurements, and even when we do, thank you, even when we do, our sample sizes tend to be small. And given what we know about the limited power that those small samples give us in being able to detect those exceedances, we have a problem. So how do we fix that problem? One way is to give comparable weight to the quantitative measurements or exposure measurements, modeling, which includes mathematical modeling, statistical modeling, and deterministic modeling, simple rules of thumb or heuristics, and professional judgment. We want to take all that we can know, use all the tools to synthesize our judgment about the exposures. Okay, so this is really just kind of a visual of what I just said. But again, we use this in a systematic way, and I won't have time to go into the specifics of how we're using the Bayesian approach, but we do recommend using a Bayesian approach. We start with a qualitative assessment, or using some kind of validated modeling. We're using the term qualitative versus quantitative pretty narrowly here. So in this context, when we talk about saying it says qualitative versus quantitative. When we talk about quantitative, we're specifically referring to exposure measurements. Our models are certainly some of the models are quantitative, but in this case, we have our preliminary judgment, or our prior in Bayesian terminology, that is developed from information from our models, from our other tools. We have we can then kind of evaluate or validate that prior information with our exposure measurements, and then we can arrive at a posterior judgment. We can refine that judgment with incorporating all of the information and using the objective quantitative measurement data to validate so that we arrive at an integrated exposure assessment. We use professional judgment. So we're using these tools to inform our professional judgment. We're never substituting, we're never blindly substituting the output of a tool for our professional judgment. What do I mean by professional judgment? The application and appropriate use of knowledge gained from formal education, experience, experimentation and inference, and an analogy. So we're really talking about the capacity of an experienced professional to draw correct inferences from incomplete quantitative data, because we're always going to have incomplete data sets, and frequently on the basis of observations, analogy, and intuition. So again, we want to have this integrated approach and ensure that we're drawing the correct inferences. So we want to make sure that we're drawing from the kinds of tools and using those tools in such a way that we're empowered to do that. So we need both the experienced professional who's knowledgeable on how to use the tools and able to draw the correct inferences from those tools. All right. Yes, as I mentioned, we generally only have data for about 2 to 5% of our exposure judgments. I just want to show you I'm going to move through this very quickly in the interest of time, but these 4 figures are from 4 different studies that were conducted, and they're just a subset of studies that were conducted over about a decade. Most of them were led by Perry Logan, so some of you know Perry. These are studies that were done with industrial hygienists, practicing hygienists, and they were presented with a series of data sets ranging from 0 up to, I think the upper value was 20 measurements. And for each data set, they were asked to make a judgment about the acceptability of that exposure. So they would be given an exposure limit and some exposure measurements. So in this first graph on the left, and again, the outcome's similar across all of them, but let's just focus on this left one. So focus on these yellow columns. Our y-axis is the percent of judgments. So this is sort of and it's the percent of judgments. So we're counting these and then categorizing them. And our yellow, the columns in yellow represent the pre-training judgments. The column in the middle of this graph represents the correct judgments. So where they predicted the exposure category following the categorical framework that I showed you, they predicted an exposure category from the data set they had. And if their prediction matched the true exposure category, then their judgment was counted in this center bucket, which the x-axis says, you may not be able to read it, it says correct. I showed you a framework with 4 categories. So if the exposure category, the true exposure category was a 4, and the participant said they thought it was a 1, then that would mean they could be off by as many as 3 categories, right? In that case, if the correct judgment was 4 and they were off by 3, then their judgment would have been counted in this far left bucket, which is labeled 3 below. And conversely, if it was a category 3 and they predicted a category 4, so they overestimated by 1, it would be counted in this column here that says +1, so on. So you get the idea. If we look at these, these yellow columns for a moment, we see that the number of judgments that were correct hover right around 40% across all the studies. So 40%, less than half the time, given these data sets, the hygienists were correct, which is really bad news, but it gets worse. We also see that there's a greater propensity to underestimate the true exposure than to overestimate. So clearly there is a need to move away from this practice of making decisions based on very small data sets, or to making decisions without the kind of systematic approach. There's some good news to these figures, and that is following some training on some kind of fundamental rules of thumb and how to kind of do a quick and dirty statistical analyses. We see that the exposure judgment improves, and in fact, when hygienists use the statistical tools with data sets, the accuracy improves. So the takeaway messages from these studies was that hygienists don't typically use the tools. They tend to eyeball the data, and that using the tools improves exposure judgment. So we definitely want to use the statistical tools when we have an exposure data set, a robust exposure data set to do that. Okay, but now let's focus on the bigger piece of the pie. What happens when we don't have exposure monitoring data? This is a similar kind of figure as what I showed you before. So the same setup, the percent of judgments are on the y-axis and the same categorical classification is shown on the x-axis. So again, if we look at the center bucket, correct? We see that when we don't have exposure measurement data and we are not using a systematic approach to estimating that exposure, the correct judgments hover around 30%. And again, this value and this trend has been replicated many times over. And as with the previous figure, that the story does get a little worse. Not only are the exposure judgment accuracies really low, they're not better than random chance. So if we're not going to be systematic about the exposure assessment approach, we'd be farther ahead to flip a coin. Don't do that. I'm not recommending we do that. We have better ways. Okay. I've used this term acceptable a whole bunch of times, and I've talked about how there's different ideas of what acceptable is. Now I want to get your input, see how you're thinking about this. So on A is no exceedances, so 100%, okay? Very good. Okay. So again, this is really, really interesting. We have, most people are settling on this less than 5% exceedance, but we still have a significant fraction of our participants saying that there should be no exceedances. Which, because it leads into what we see this a lot. We see that there are variable definitions of acceptable across, and that's across our profession, people with similar training and similar experience. And we have variable definitions of acceptable uncertainty. And as we saw a moment ago, well, it's not absolute consensus. Many settle in on this idea that a 95th percentile with a 95% confidence is what most people think we should use as a definition of acceptable. So I'm going to talk now about structured approaches to decision making, and I'm going to cover a couple of the algorithms used in the tool. But first, I want to talk about why. Why are we recommending this approach? We can learn from our colleagues in psychology. So there are a number of studies that were conducted by Nobel Prize award-winning psychologists that showed us that when we are systematic and transparent in our assessment to make a decision in the face of uncertainty, that our exposure decisions are more accurate. With focused training and coaching, they improve. With accurate feedback mechanisms and repeated practice, our exposure judgment accuracy improves. All right, so I'm going to show you a little bit of evidence in a minute, but I'm also going to spend the bulk of the rest of the time talking about this tool that follows this approach. It follows a checklist approach. And the reason is that by following this checklist approach, the tool focuses us on using objective and relevant inputs in an ordered fashion to produce accurate and consistent outputs. It applies to a broad range of scenarios. It's really easy to use, and even easier with the newer version, the Structured Deterministic Model 2.0. The model, the Structured Deterministic Model, or SDM, applies simple algorithms to improve exposure judgment accuracy. In fact, it uses three fundamental algorithms that are based on physical chemical principles that were developed empirically over many, many years. So developed and refined over many, many years. The tool is structured like a checklist. So, by following the same approach, the same kinds of inputs in the same order, then we are assured of consistent application. We use the tool consistently, we consistently get good results. All right. So this figure, again, same layout, percent of accuracy, percent of judgments on the y-axis, and then in the center grouping, we have the accurate or the correct decision, the correct decisions. And so so again, this is evaluating exposure judgments made without the benefit of personal exposure measurement. And just to be clear, so this is a study that I conducted with my team. I had the exposure measurement data, so I knew what the 95th percentile 95th percentile value was, but my study participants didn't. And so if we start by focusing on these gray bars, and again, I'll be very brief in the interest of time, we see a similar trend, right? We see accuracy hovering around 30%, not statistically different from random chance, and a tendency to underestimate the true exposure. But the really exciting news came following our study evaluation of the use of the tool. So following the use of short training and use of the tool, look again at that center column. The percent accuracy by the same group of hygienists literally doubled. So it increased to just a little over 60%. And if we included accurate or overestimating by one category, the accuracy was in the range of 70-something%, which parallels what we see with the exposure judgment accuracy of hygienists when they have a robust data set. So it gives us tremendous power. Okay. In the same kind of study, but in this time, working with students. So for all you students here, give yourself a little pat on the back. Students actually performed a little bit better. So their baseline accuracy was a little over 40%. But what we didn't see in their judgments was the bias towards underestimating true exposure. Students had not yet picked up our bad habits. They hadn't been miscalibrated. It's what we think was happening. We see a much more balanced approach to overestimating and underestimating. We also saw a nice increase in the exposure judgment accuracy of their judgments when they were trained on the tool. So again, to a very similar level as what we saw with the practicing hygienists. And so the significance of this is really, really huge. In a sense, it's an equalizer. We were able to put this tool in the hands of brand new hygienists or soon to be practicing hygienists, and they were able to make exposure judgments with the same level of accuracy as their counterparts who were CIHs and ROHs and had years of expertise under their belt. All right, so about the tool. It's recommended for agents that are pure or relatively pure, volatile or semi-volatile chemicals, and for chemical mixtures. It's also used for fibers, particulates, and aerosols. There are a number of new terms that you've probably not heard of that I'll go over. So in exposure control category, you probably know that one. Occupational exposure limit is familiar. This OBS-LC, or observed or reported level of control. What that means is the level of engineering control that you would either observe in the workplace because you are able to go to that workplace, or that level of control that is reported to you. So whether it's because someone reports to you or it's in the literature, but by some reliable means, you're able to assess the level of engineering control. So that's what's the actual level of control that's present in the workplace. The required level of control is the level of engineering control that is deemed necessary to adequately control that hazard. Adequately meaning controlling the hazard to below the occupational exposure limit. So in the SDM 2.0, there are two main checklists. Checklist number 1 applies to pure or relatively pure volatile or semi-volatile chemicals and chemical mixtures. Checklist 2, that's shown here, relates to fibrous particulates and aerosols. There's a lot of, so this is the picture of the dashboard, and if time allows, I'll pull up the actual tool, but for now, I'll at least go through the screen captures. There are a lot of wonderful features here. You can size the dashboard and the screen that you see according to your operating systems by clicking on the right value here. If you click on the arrows of either one of these checklist boxes, it will take you to the correct dashboard for that checklist. There is a support file, so that's a separate Excel-based file that I'll talk a little bit more a little while again, but it is an essential counterpart to the tool itself. There's some additional reading that we recommend, a citation, and then a reference to the fact that this is licensed, reflecting the considerable intellectual property contained within the checklist. All right, so for the next few minutes, I'm going to walk through the algorithms that are relevant to checklist 1. And an example, I'll show you an example of how it's applied, but I really want you to understand the basis for these algorithms and how they're being applied. As I said, we have a recorded video that walks you through step by step on how to use the tool. It's pretty user-friendly, but it's essential to understand what these algorithms are doing and how they work. The first one I want to talk about is called the rule of 10. And in order to talk about the rule of 10, there are some kind of fundamental facts about vapor pressure that we need to review. So when we talk about vapor pressure, we're talking about the pressure that's exerted by the gaseous phase of a two-part system. So gas liquid or gas solid. And the vapor pressure is the pressure that's formed above that liquid or solid. If the substance is in an enclosed place, like a container, then given enough time, that two-phase system will arrive at an equilibrium state. So we get this dynamic balance condition in which neither phase in that system will change. And at a specific temperature, the vapor pressure measured in that equilibrium state is called a specific term called saturated vapor pressure. So when we talk about saturated vapor pressure, it's that vapor pressure of that equilibrium state. And the vapor pressure is a fraction of the total pressure being equal to 760 millimeters of mercury at sea level. Vapor pressure is temperature dependent. So the temperature changes, the vapor pressure is going to be, the vapor pressure will change. And that's really, really critical. So I'll say it again. If the temperature changes, the vapor pressure will change. So you need to be aware of that. When you're comparing vapor pressures across different agents, because of this temperature dependence, it's really important that you make sure that you're comparing vapor pressure values of those agents at similar temperatures. The vapor pressure at an agent's boiling point is 760 millimeters of mercury. That's especially useful for dealing with non-ambient conditions, which I'm not able to go into today, but I will mention that we offer a 2-day professional development course at the AIHA conference. We'll be offering it this year, in which we go into detail about all of these things. As well, as I mentioned, we have the recorded learning modules, so there's more information there. When we have chemical mixtures, the vapor pressure of that specific agent or the specific agents in the mixture will be lower than the agent's vapor pressure in its pure state. So in a mixture versus a pure chemical, the vapor pressure will be lower. And very briefly, vapor pressure and boiling pressure are usually reported on the safety data sheet. So you can find that data there. You can also find it in online resources such as PubChem, the Hazardous Substances database, or the NIOSH Pocket Guide. Okay, so the rule of 10 takes advantage of this saturated vapor, or the vapor pressure, and we can calculate the saturation vapor concentration, which is the product of the the ratio of the vapor pressure expressed in millimeters of mercury divided by atmospheric pressure, which conventionally is 760 millimeters of mercury at sea level. And then I'm gonna blow this up a little bit, so hopefully you can read it a little bit better. This is one of those algorithms that has been refined empirically over many years. And the idea is that for every incremental increase in the level of control, the fraction by which the saturated vapor concentration is reduced by a specific fraction. So in other words, the maximum concentration that we would expect to see is reduced by about an order of magnitude. So if we start with, completely enclosed space, then we might see the saturated vapor concentration. But in an environment where there's good general ventilation, so indoors, or in protected outdoors where there's minimal wind, we would expect to see a concentration that is about 1/1000 of the saturated vapor concentration. And it turns out that's very, very useful information because we can almost always obtain the value of the vapor pressure. So as long as we can then get some sense of what the level of control is in the workplace, and we have some sort of exposure limit or some benchmark to compare it to, then we can make an assessment of exposure, both quantitatively, so as a concentration, as well as categorically. Yes, sir.
Can I ask a question, or I don't want to interrupt?
Is it a clarifying question about what's on the slide or just conceptual?
Just on the slide.
Okay.
It really relies on knowing the size of the room. Otherwise, if you're just in open area, you cannot really consider that because it's saturated concentration.
Well, it actually depends on the ventilation in that room, as it turns out. There are some exceptions, but more or less, but by and large, this is actually quite accurate.
Okay.
Yeah, we'll come back to some of the exceptions. I just wanted to reiterate that the rule was developed from empirical observations of exposure scenarios where quantitative measurements were available. So it was calibrated using real exposure measurement data. And using this rule of 10, the outcome is a point estimate of the 95th percentile. So here are the steps that go into the application of the rule of 10. And I'm going to walk through these quickly, but know that in the structured deterministic model itself, many of these steps are automated for you. So we begin by selecting an appropriate occupational exposure limit. So whether we decide we want to use the ACGIH-TLV or perhaps an internal occupational exposure limit, we start there. We look up the vapor pressure or estimate the vapor pressure of the agent of interest at the temperature of the system, the source that is emitting the vapors. And with that, we can calculate the saturated vapor concentration. We identify the observed level of control. So again, whether we directly observe it or it's reported to us. From that information, from the level of control and looking up from a rule of 10 table, we can determine the fraction of the saturated vapor concentration that we would expect, which allows us to calculate the maximum concentration that we would see. And again, we're using that as a surrogate for a 95th percentile. So we would compare that value with our occupational exposure limit or benchmark, and then we can convert that concentration as a fraction of the OEL to an exposure control category. So we can express this categorically as well as quantitatively. So let's just walk through an example to see how that would work. So let's suppose we have a scenario with acetic acid, and we decide that we're going to use the ACGIH-TLV. 8-hour time weighted average is 10 parts per million. So knowing our, we look up our vapor pressure for acetic acid at the relevant temperature. We see that it's 11.25 millimeters of mercury. And then applying our equation for the saturated vapor concentration, we end up with a value that's 14,800 part per million. So in a completely sealed compartment, the maximum concentration that we would expect to see is about 15,000 parts per million. We know that in this scenario, there happens to be good general ventilation, which quantitatively equates to about 5 to 6 air changes per hour. Then going to our table, we see that that equates to a reduction, about a 1/1000th reduction relative to the saturated vapor concentration. So applying that value, we see that the expected concentration that we would see, again, this is a point estimate of the 95th percentile, would be 14.8 parts per million. It's pretty straightforward. And again, we can convert that so that our 95th percentile value, we can compare that to our OEL, and we see that compared to our OEL, we have a ratio of 1.48 or 148%, which would equate to a category 4, because above the OEL would be a category 4 exposure. And then again, it's within a factor of about 1 to 2 times the OEL. And so if we were looking at respiratory protection, that would we would need an assigned protection factor of 10. Okay. All right. So this is the dashboard of the tool. When you open it, this is what you'll see. And I would click on this checklist 1 to look to use the algorithms for a chemical. And I'm just going to walk through kind of generically how one would use the tool, and then I'll walk through an example. So as I mentioned, checklist 1 is for the volatile and semi-volatile chemicals and chemical mixtures. Thank you. The input steps are numbered. So remember I said it's like a checklist. So so the tool is numbered step by step, so you can see what order to input the information. And then you're further guided by these shaded cells. So the green cells are your input cells. These are the ones that are not locked down. Let's see, I guess I can't enlarge that. We have the drop-down menu from which you can access an embedded database that has a list of chemicals, as well as relevant chemical property data that will allow us to very quickly populate some of these other fields. We have several options for either identifying or estimating the vapor pressure. And again, I'm not going to go into the specifics now. I'll go into this in a little more detail when I talk about chemical mixtures. We have a number of options for selecting the occupational exposure limit. And so to help us be aware of what those options are, on the bottom part of the table, there is a display that shows us the different agencies that set occupational exposure limits. And so for OSHA and NIOSH, and then also for some of the EPA AEGLs, once we identify the chemical, if there are exposure limits set by those agencies, those numbers will appear in this table. There's an extra step required for ACGIH TLVs. So ACGIH TLVs are protected intellectual property. But if you click on this little button that says Hub on it, that will take you to the Data Hub. And more specifically, again, once we would do this after we've identified our chemical. So once we've identified that chemical, the Hub button will take you to the ACGIH page, Data Hub page for that chemical. And I think, yes, if you happen to be a member of ACGIH, then from that menu, you can also access the full TLV documentation. So you get access to a very robust risk assessment package. Okay. So in this example, I've just pulled up a toluene case study where we have our operational temperature, our relevant temperature of our vapor, or the liquid emitting the vapor is 25 degrees C. I've indicated that I want to use the embedded SDM database. There is also an option to set up a users database. I've selected the chemical toluene, and when I did that, you can see that these green cells have values, the number of the values are populated. So we have a CAS number already identified. We have a value for the vapor pressure identified. We have the molecular weight identified. I have pre-populated this with the weight percent, and in this case, I've indicated 100%, representing a pure chemical, a pure substance. If I was going to look at a chemical mixture, then for each component in that mixture, I would indicate the weight percent of that component. And then I would transfer the data to the table on the right. And basically, I'd build my recipe until I had all the information entered in there. From the selection of occupational OELs, so again, this is one of those areas where your professional judgment is needed. You need to decide what is the most appropriate OEL for your exposure scenario, and then you manually enter it into that green cell. When all of the necessary data has been correctly entered, we have a little emoji to help indicate that we have achieved that. So with a happy face, we can then click on the transfer arrow, which moves our data to our table. In the case of a pure substance, there's nothing more to do. We're ready to go to the report page, but with the mixture, we would iterate through this step until we had a recipe built. As you can see here, I've transferred the information. It's all there. We have a happy face, tells me that I'm ready to go to the next step. So I click on the red arrow at the top of the dashboard, and I would then get a confirmation message telling me that the data has been transferred to the calculation sheet. And then the tool will automatically transfer you to the report page. The report page has been formatted to be a single PDF, a single page, which can be saved as a PDF, so that you can save both your inputs and your outputs, which is extremely helpful for those of us will get so excited about the output, we won't necessarily remember what our input values were. So we can see all of the data here. We have some free text space at the bottom where we can input comments or any particular facts or notes, observations that we want to capture for later. On this dashboard, let's see. Okay, yeah. So taking a little bit closer look at the report tab, so there's a lot of information here. The input data is transferred from the input table. So in this case, we have the name of the chemical, the molecular weight, the CAS number, and so on. I just want to, so the exposure level, so again, we get a quantitative estimate of the exposure based on the level of control that we've indicated, but we've also set up this report so that you can see what the concentration would be if the level of control was different. So we just find it really helpful to be able to look at the various types of engineering controls, both for our own knowledge, as well as for communicating with our managers and workers, and educating. It's just really helpful to see what that would look like. Similarly, we have the exposure categories that are derived from the concentrations relative to the OEL. And again, we show all of the possibilities with the actual predicted exposure category highlighted, as you can see here. This tool looks not only at exposure, but also health risk. So on the report tab, you have the opportunity to enter a health effects rating, which you indicate numerically here. There are a number of frameworks that are out there for providing criteria as to how that numbering system can work, you can also create your own. The observed level of control is selected on the report tab from the drop-down menu shown here. And then, as I mentioned, the exposure control category is shaded, so it shows you the impact of the different levels of control on both the concentration and the exposure category. You know, if you're making a case for upgrading engineering controls, this is really helpful. It's just so visually informative. And then because we have inputted the health exposure rating, health effects rating and estimated the exposure, then we're able to produce a health risk ranking matrix here and express our assessment as in risk terminology, both visually and numerically. So far, mostly focused on pure chemicals, but as I mentioned earlier, with chemical mixtures, we have that recipe approach. And so if we are looking at a chemical mixture, we see additional information provided on the report tab. So we see the molecular weight of the mixture. We see some additional information that I'll talk about in a few minutes and explain why that is useful. And again, we get the exposure control categories and health risk rating for each component, as well as for the overall mixture. And that's really helpful because if you have, for example, if you have a chemical like benzene, where you have specific requirements that are in the standards, so that you are compelled to do, if you have that chemical in your mixture, you really need to know that information at both the chemical level and the overall mixture level. All right. In the interest of time, I just want to mention that there is a companion file that goes with the tool. We call it the support file. And in it, it provides the basis for all of the algorithms that we use, and basically for everything that is in the SDM that contributes to the derivation of the exposure and risk values and outcomes. We have a number of we have some calculators so that when you need to estimate values, for example, under non-ambient conditions or convert values, that's all in there. The guide, as I said, tells you about the basis and the application with some case studies of how to apply these things in the very messy real world. We have reference values for the substances according to the various agencies that set occupational exposure limits. And then we have some additional administrative material. You can see that some of these are grayed out, they're in gray font, which means they're not yet active. These are areas that we're still working on developing. Okay, so I have until, okay, 15 minutes. I was going to present an example showing the use in the tool. I'm going to skip over this because I want to spend time talking about one of the other algorithms that pertains to checklist 1 and to especially useful for chemical mixtures. And that is the vapor hazard ratio. So the vapor hazard ratio is the ratio of the vapor pressure. So for a pure substance, it would be the vapor pressure of that pure substance in millimeters of mercury divided by the occupational exposure limit. With mixtures, which I'll go into in more detail in a few minutes, that vapor pressure is going to be adjusted to account for it being present in a chemical mixture, and I'll explain more shortly. Okay, so I'll illustrate this with an example. So let's say we have a mixture with the compounds you see here, and the corresponding composition with the weight percent in the right-hand side of the table. So the toluene is present at the highest concentration at the highest weight percent of 40%, and benzene is present at 2% with some other constituents in. So in this scenario, where we have 6 chemicals, 6 solvents, we have to make an assessment of the acceptability of the exposure of this kind of mixture. we're likely not going to have the resources to go out and measure the exposures to each of these chemicals. Would you agree with that? Yeah. So, what do we do? How do we handle this? Do we assume that the chemical is that's the largest component by weight? That one would have the highest exposure, and therefore we focus on that. Should I look at the chemical with the lowest occupational exposure assessment? Perhaps, sorry, occupational exposure limit, perhaps assuming that that relates to the most toxic compound. Should I look at the chemical that has the most significant adverse health outcome? Or should I look at the most volatile component, so the component with the highest vapor pressure? Do I need to look at all of them? Or do I find that's all too overwhelming and just say it can't be done? Well, in fact, we do have a systematic approach to this. And in order to apply it, there's some fundamental information that is needed, but all of it is obtainable. So starting with the weight percent, which I already showed, we need an occupational exposure limit for each of the components. We need to know the molecular weight of each component so that we can calculate its mole fraction in the mixture. And we need to know the vapor pressure of the pure chemical. And in this case, I said at 25 degrees because we're looking at a scenario at 25 degrees. And now to apply the vapor hazard ratio appropriately, we need to adjust the vapor pressure to account for the chemical being present in chemical mixture. And there are a couple of ways we can look at this, or we can estimate the adjusted vapor pressure. So using Raoult's law or Henry's law. And with Raoult's law, we express that adjusted vapor pressure. So the vapor pressure of the component in the mixture by multiplying the mole fraction of that constituent by the vapor pressure of the pure component. With Henry's law, sort of similar, we estimate the vapor pressure by looking up the Henry's law constant for that component and multiplying it by the molar concentration of that component in the mixture. There are specific criteria for when one is preferred over the other. Dr. Abaton mentioned that this morning. I won't go into it, but again, there's a whole module that will explain when and where it's best to choose one versus the other. We have also been having discussions about the benefits of using both and comparing the predicted vapor pressure. All right, but back to our question at hand. When is a component, which controllant is controlling? Controlling compound means that in a mixture, we want to know which component has the highest potential to exceed its corresponding OEL. Because if we control for that component, then we have essentially looked after all of the others. If we adequately control the controlling component, then we will have adequately controlled exposure to the others. So it's a very efficient way of addressing the potential exposure to multiple components. So the tool will do this for you automatically, but I just wanted to show here that given this particular mixture, if we had gone with looking at or basing our decision on the component that had the highest weight percent in the mixture, we would have not identified correctly the controlling component. So we're looking here at the relative percent here. So in other words, the likelihood of that component to exceed its OEL. And we see that with toluene, we have a 12% probability. But in fact, if we look at benzene that was present at only 2%, given its OEL and its vapor pressure in that mixture, there's actually 100% probability that we would exceed the occupational exposure limit. So we need to make sure that we're controlling for benzene. We look after that one, then we will have control of the other compounds. Okay, just very quickly, we have calculated the adjusted vapor hazard ratio. So remember, the vapor hazard ratio was the vapor pressure divided by the occupational exposure limit. And with a mixture, we would use the adjusted vapor pressure to account for that constituent in the mixture. So we can calculate this adjusted vapor pressure for each component. And then we can also calculate, we do calculate an overall adjusted vapor hazard ratio. So with that vapor hazard ratio from mixture, which the value was 8.3, that corresponds to a vapor hazard ratio scale of 3. So this is in our vapor hazard ratio table, which I haven't showed you here, but it's in the tool. But from that table, so again, this is a table that has been empirically refined over many years. And so the table tells us that for a scale of 3, that in order to adequately control the exposure of benzene and the mixture, that we would need good general ventilation and capture local exhaust ventilation at the emission points. So a lot of information gathered from the tool applying that vapor hazard ratio with the mixtures. Checklist tool 2 is, again, very, very useful, very powerful. It's much more straightforward. It stems from the performance-based exposure control framework that was published by Bruce Nauman in the late 70s, I think. And again, it's a heuristic that has been refined over many years. And the way it works is that you start by identifying the range within which the occupational exposure limit for the agent of interest falls. And then having identified that range, there's a corresponding PHR scale that corresponds, again, with a specific required level of control. So the first step in using the tool is to identify the range within which the OEL falls. And the second step is to identify, through a drop-down menu, the observed level of control. So you're indicating what you see or what you've been told is present in the workplace. And then from there, a decision logic is applied. So the tool is going to compare the required level of control with the observed level of control that you indicated was present in the workplace. And the logic is going to predict a category 1 if the level of engineering controls that you observed in the workplace is more stringent than what is required. It will predict a category 2 if the observed level of control matches the required level of control. And then if the observed level of control is not as stringent as what is indicated in the required level of control, then the tool will predict a category 4. You'll notice perhaps that we jumped over category 3 that has to do with the nature of the Bayesian analysis and the level of uncertainty on our part on how to appropriately address that. So in the spirit of being health conservative, we've erred on the side of overestimating some of the exposures. Just to give a quick example, so let's consider this clean room environment where the operator is working with lithium cobalt oxide powder, and he is weighing some of that powder before he transfers it to a blender. So the tasks are weighing and mixing, conducted in a clean room, where the contaminants are, in theory, removed by a large slot hood. The air exchange rate is about 2 per hour. So again, walking through the process, the ACGIH short-term exposure limit for cobalt is 0.02 milligrams per cubic meter. And so that tells us that that would fit into this range And based on our vapor hazard ratio, particulate hazard ratio matrix, that would indicate that capture is the level of the required level of control. And since the required level of control is capture, but what we observed was general ventilation, then we would see, in applying the decision logic, that this would be a predicted category 4, which I know from exposure measurement data is correct, that it is an exposure category 4. So again, we have an example. I think there isn't really enough time to go into the tool to show you this, but there is 5 minutes for questions. I gave you the link to access the tool, so you can download it and license it, and I'll give you the link to the recorded narratives. We do have our PVC, but again, if there's interest in having like a 1 hour just focused on, okay, let's just pull the tool up and go through case studies. We love doing that, and we'd be happy, we'd be thrilled to be invited back, either in person or remotely. So again, with that, I welcome your questions.
Well, questions from the local audience? Any from the online audience?
Je viens de just ask the question if there are questions. Pas encore.
Maybe, can you come back to the VHF of the mixture? The example with the benzene and yes, this one. Here, for the adjustment for the VHF, is in line with the VHF for the pure substance? And you make the correction regarding the mole fraction, is exactly?
That's right, yes. So the default in the tool right now is to make the adjustment based on Reynolds law.
So the vapor pressure, say for benzene, we didn't use whatever it was 95, we used whatever was the corrected vapor pressure. Then that's what we divided by the OEL.
The OEL.
And then the column H, that's the actual vapor hazard ratios. And column J is you take the largest one and you divide each one by the largest one. So it just jumps out at you. That's what this is, it's benzene. And the other thing it tells you is, like in this case, if benzene didn't come out to be at its OEL, carbon ket would be, its OELs, I think benzene at O2, O5, with carbon ket, it would be roughly 50% of its OEL, which was 5, and so the carbon ket concentration would be about 2.5 parts per million in this mixture. If benzene was, if the measurement was 0.5.
So
We got a whole section that we talk about that.
Yeah.
The controlling component, and it's the engine behind why that all works.
So there's a lot that can be done with and from the vapor hazard ratio, which again, Mark spent a lot of time in the PDC covering, just time didn't allow for this today. But it's very, very versatile. Daniel?
I just want to mention that for a normal user, after 30 minutes of formation, you can enter an example like that in less than 10 minutes. And the next would be even faster. So it's very easy. And if somebody wants a demonstration after the presentation, I can do it.
There's a question here from Kevin Hedges saying, has there been a comparison with COSHH essentials?
Oh, hi, Kevin. No, we have not yet. We have not compared this to COSH essentials. There was another question? Yes, sir.
I wonder to which point the process as well, or the activity is considered in the equation. Let's say you have a barrel here, which top is open with this mixture. So there's something I can do if someone is working next to this barrel. But if the same product is being applied by brush on the floor to say the paint, or it's sprayed, so at some point this equation or this equation may not come to the same conclusion.
So no, those are very good points. So if it was sprayed, then it would become an aerosol. And then one would be compelled to use the checklist 2. But certainly, I mean, like you're right, like intuitively, we know if somebody has a near field exposure versus someone who is much farther away, there will be difference in the concentration. So there are some specific conditions in which the tool may overestimate, or especially for short-term exposures, you have to think about whether it will be representative, like with really, really small quantities is another example where if we have a very small finite volume of a substance, then we're not clear that we're not going to reach saturation vapor concentration, and therefore using the rule of 10 we'll still be overestimating. But for the most part, I mean, depending, it's agent specific. So if it's such that like a highly toxic volatile chemical is going to require some sort of perhaps capture or LEV. So some of that is reflected in the level of control that is required.
In that one chart that had very fine verbiage, there is some guidance, and we give them guidance. Say if someone was filling a drum, obviously the exposure is wrong. We correct for that, and we adjust it for different things. One of the big things, SDM 2.0 is not supposed to take place by H5. Once you're good at this, you can do one in probably on the order of 1 to 2 minutes. Include a mixture in 1 to 2 minutes. If you get to H5 2.0, you're probably in the order of half hour or an hour, which is still very, very fast. Now, it gives you better resolution, but it takes longer. And so if you got a mini to do, what you want to do is something really quick. And if you have uncertainty, then kick it to a higher level evaluation. Yeah. So it's not supposed to be handled just by itself in a vacuum. It's all these tools are coming together, and you use the judgment of IH. Well, I'm still uncertain here because just like you mentioned, well, I'm going to go to another level, and you keep going to another level until you're satisfied. So,
and I just wanted to add on to what Mark said. The other compelling motivator to developing this tool was that because I used mathematical models for many years in my practice, but we were so frequently limited with not being able to find values for emission rates and other critical inputs to the model. And so I wanted us to have a tool that would be useful in at least providing a preliminary estimate of the exposure using inputs that were certainly relevant, but that were more readily available. And this tool just requires very few inputs that typically can be either readily sourced or can be readily estimated. But absolutely, back to Mark's point, we need to further refine our understanding of this. If we need to refine our estimate of the exposure based on an understanding of the scenario, then another option could be to go into IH mod.
Yeah, factor I could see lately, because I know I use these mod fact equations, but I had this site the other day. I think it was methyl methacrylate that has a vapor density of 3. And at some point when you measure at the respiratory level, you measure like under the PEL. But as soon as I saw some guys doing touch-up close to the floor, I went to measure and they were in IDLH. So there was a huge difference in concentration just due to the vapor pressure. So there are definitely some situations, as you mentioned, expressed, that this equation or this assessment cannot be necessarily practical because you have to consider other physical property.
And that's one of the points we're trying to make,
Yeah.
that IH is not plugging into some kind of formula.
Yeah.
You need to understand the workplace, that's basic characterization of what's contributing. And, you know, where you are, like, or if you got chlorine compound, they're gonna be on the floor or close to it.
Yeah.
And should you consider that or not in that? But that's all the knowledge we should be building in our IHs, that they understand the capabilities of the ventilation and the characteristics of the molecules. Where are the molecules? They're gonna be higher, lower, whatever.
What is interesting also is you can use SDM 2.0 in a kind of what if mode. So you can launch your example and redo the same example with different OEMs. The table you saw, the values of the OEM, for benzene was 0.5. ACGIH released its new TLB at 0.02. Imagine the change and the change in the judgment you may have. So you can change any parameter. And I know that Mark is eager to see the version 3 of SDM 3.0 in order to quickly change some parameters of the scenario, just as he did with IH1 2.0. I think he is the master of IH1 2.0 now.
Yeah.
Even better than me.
All right, so as you might have noticed, Susan left, but he has a call. But so the seminar is officially over, but you are free to continue discussing and arguing, and you know, because we like people to exchange views, and so this is great. Please feel free to stay and discuss. Those who prefer to leave can leave too. Yes, so and Susan is working in our office. So thank you very much for being here. And now the floor is open for free range discussion.
Thanks for that.
And yeah, sorry for the people online. Thank you for your attendance, and please come to the next seminar from CESP, Centre de recherche en santé publique de l'Université de Montréal.